Hi, good evening everyone. Welcome to the course NPTEL course on basic construction materials, and we are now at the level of week 9, and week 9 lecture pertains to the polymers. Till now we have seen different types of construction materials like cement, concrete, steel, etc. Now we are going to deal with polymers. Okay, the week 9 lecture pertains to polymers and plastics and composite materials. See, what do you mean by polymers? You would have heard it uh, before before you joined your graduation. You would have heard it. What do you mean by polymer? It is a chain of many units. It is a chain of many units. For suppose here you are able to see this polymer is equal to many mers. Mer is nothing but an unit. For suppose if you have a single unit of this of this element, you can say it as monomer, and if you have two units of this, then you can say it as dimer or trimer, etc. But if you have multiple units of this, for suppose in polyethylene you have units of hydrogen, carbon and hydrogen. Okay, and if you have many units or many mers of this kind, then you can name it as polyethylene. Here instead of one atom of hydrogen, chloride atom is replaced here, and this is known as polyvinyl chloride, and this is polypropylene. So polymers are nothing but a chain of many units, a chain of many units. Okay, that's why it is known as polymer. Poly means many. Okay, and this will be in the form of the configurations will be in the form of chains, like covalent chain configurations and strength. See, there are different types of configurations in this polymers. Here the first one is linear. That means many units are linked are formed in the form of a chain, and the two chains are connected by secondary bonding. Secondary bondings are nothing but the weak bonds which are covalent bonds. Okay, and this is the linear type, and this is branched means like from the see these are the two main chains, and from those main chains some branches are coming up. Here it is cross linked. That means the chain of polymers, for suppose here you can see three chains of polymers, 1 2 and 3, and these three chains are interlinked with the other small chains of polymers. That's why it is known as cross linked. And here it is network or reticulated polymer, network or reticulated configuration. That means the chains or atoms are organized in an orderly manner here. So from this you can understand, like if you want to define the strength of each configuration, then uh, you can say that from linear to network, the direction, it is in the direction of increasing strength. It is in the direction of increasing strength. That means linear will have very lesser strength compared to this network or reticulated. You can understand from the figure itself. See, in linear case you have secondary bonding which is weak bonding, weak covalent bonds. So here the strength will be very less. In case of branched, even though the branches are coming, but they are not interlinked with each other. They are not interlinked with each other. And when coming to the cross linked configuration, here the chains of polymers are interconnected with small chains of polymers, and here everything is interconnected in network or reticulated. Okay, so that's why from linear to network or reticulated configuration, you can see that is in the direction of increasing strength. That is in the direction of increasing strength. So now you are in a position to tell in which configuration has higher strength and which configuration has least strength. When coming to the polymer characteristics, first thing is molecular weight. Molecular weight is nothing but mass of a mole of chains. Mass of a mole of chains. See here you can see a smaller chain and you can see a larger chain. From the definition you can understand which will have a smaller molecular weight and which will have larger molecular weight. See, this is a mass of a mole of chains. Mass of a mole of chains. Here, as the size of the chain is very smaller, the mass of the mole of chains will be less. So molecular weight will be smaller. And in case of larger chains, the mass of a mole of chains will be higher. So the molecular weight will be larger. And on this molecular weight, this the tensile strength also depends on this molecular weight. It increases with the molecular weight. Why? Because the indirect reason for the increase of tensile strength with molecular weight is, see, if you have larger chains, for suppose the chains are all like they are interconnected in the shape of a sphere or a round ball, then you can say if you have larger chains, what will happen? The interconnection will be more. See here, the longer chains are entangled or anchored better. So when you have larger chains, they are entangled or anchored better, right? This is a simple logic. For suppose if you have a larger length of some thread, and smaller length of thread, by using which length, like larger or smaller length, by increasing which one we can get the higher anchorage. Obviously by using the larger thread you can get a higher better chances of anchorage. That's why with increase in molecular weight, tensile strength also increases. And coming to the another characteristic, percentage crystallinity. What do you understand by this crystallinity? See here in this figure you can see this is the crystalline region and this is the amorphous region. The amorphous region is in a irregular manner, whereas the crystalline region is in a regular pattern. Is in a regular pattern. So percentage crystallinity is nothing but percentage of material that is crystalline in nature. For suppose here you can see the regions of crystallinity here. So there is some percentage of material which is crystalline in nature. So that is known as the percentage crystallinity. Okay. So what is the importance of this crystallinity? Tensile strength and elastic modulus often increases with percentage crystallinity because it is arranged in an orderly manner. When it is arranged in an orderly manner, obviously the tensile strength and elastic modulus will be higher, like the mechanical properties of the material will be higher. And what causes the crystalline region to grow is annealing. Annealing is a process in which the material is heated to a temperature like higher than its recrystallization temperature, and then it is slowly cooled down. So by doing this, what will happen is the number of crystalline regions will grow, and thereby the strength of the tensile strength and elastic modulus of the polymer will also grow. That's why the percentage crystallinity is important here in case of polymers. And coming to the discussion of molecular weight, as we observed in the last slide, what you have understood, like the smaller chain will have smaller molecular weight and larger chain will have larger molecular weight, right? Excuse me. So molecular weight is a function of chain length, right? Molecular weight is a function of chain length because it depends on the chain length. When you have smaller chain length, the molecular weight will be smaller, and when you have larger chain length, the molecular weight will be larger. And it is number average and weight average defined. Number average and weight average means, from the definition you can say mass of a mole of chains. Mass of a mole of chains. So you can take a mole of chain and you can calculate the mass of it, and you can average it, thereby you can get the molecular weight. That's why here it is defined as weight average, average defined, and number average means by counting the number of moles, by counting the number of moles in the chain also you can define this molecular weight. And coming to the degree of polymerization, see, as I told you earlier, if there is a single unit it is called as monomer, if there are 2 units it is called dimer, if there are 3 units it is called trimer. Okay, so degree of polymerization is defined on the total number of units. By counting the number of units only we have come up with these numbers like monomer, dimer, trimer and polymer. And what is the degree of the polymer? The degree of the polymer is defined based on the total number of units present in the chain structure. Okay, and coming to this mechanical characteristics, these polymers are highly influenced by the rate of deformation, highly influenced by rate of deformation and temperature, and then the presence of water, oxygen, organic solvents, etc. Right? Like, see, when compared to the steel or concrete, this polymer will have highly influenced by the rate of deformation, temperatures, and presence of water, oxygen, and other organic solvent. Because these polymers doesn't have that much strength when compared to this concrete or steel, so the rate of deformation will be higher with the sustained loading. With sustained loading the rate of deformation will be higher, and with increase in temperature the mechanical properties of the polymer will change, and with the presence of water, oxygen and some other solvents also, the mechanical characteristics will get changed for the polymer. And the 3 types of responses for the polymer are, like we have seen in the case of concrete or steel, we have already studied the stress strain characteristics, right? From the stress strain characteristics itself we understood what is meant by the brittle nature, what is meant by plasticity, and what is meant by this elastomeric. We would have seen this elastoplastic region in case of steel, but here the case in the case of polymers it is known as elastomeric, brittle, plastic and elastomeric. In subsequent slides you can understand what are the what do you mean by brittle, plastic and elastomeric nature. Okay, see, this is the tensile response of a polymer. This is the tensile response of a polymer. This is the stress strain curve, stress on the y-axis, strain on the x-axis, like we saw in the case of concrete and steel. Okay, see, here the green line, this line represents the brittle nature of the material, because it is like at lower strains itself, at lower strains the the stress is very higher, and it is reaching the fracture point without much elongation. It is reaching the fracture point with increased stress, so this will have a brittle nature, Okay, see, here when you take some semi crystalline case, here this represents a semi crystalline case. Here at 0 stress strain graph, at the origin of the stress strain graph, here you can say the material response is semi crystalline. It is semi crystalline, but after loading to some extent, like within the proportional limit, within the elastic limit, it is amorphous, like the region is amorphous regions elongate. So the crystalline regions will stay as such, but the amorphous regions in between will tend to elongate and at this point, like this is the yield point, right? So at the yield point what will happen, the crystalline regions will align, and after that with increased loading what will happen, this is onset of necking, and with increased loading it will reach a point like plastic failure. This is plastic failure, this is not a brittle failure, this is plastic failure. That means the with increased strain rate it is reaching the failure at some point, like not like this brittle failure. So in the this is the near plastic failure, near the failure region. How it is, see, before the plastic region, after this yield point, these crystalline regions are sliding against each other. The crystalline regions are sliding against each other, and near this plastic region, you can see how the material has got deformed. How the material has got deformed. So, like the tensile response of a polymer is depicted in this particular graph and the figures here. So brittle behavior is common at low temperatures and high strain rates. High strain rates and at low temperatures the brittle behavior is common. So for the polymers, the brittle behavior is common at low temperatures, but when you increase the temperature, you can see the you can see the plastic nature of the polymer. For suppose if you have some plastic material, like plastic is nothing but it is made out of some kind of polymers. If you say have some plastic material, and if you increase the temperature, if you increase the temperature at which the plastic material is located, you can see initially the plastic will be in hard. Initially the plastic which is in hard state will tend to soften with increase in temperature, and means from solid it is coming to the liquid state, like semi elastic stage and then liquid stage, right? So the brittle behavior is common at low temperatures but at high strain rates. See here, the material is elongated near this plastic region. The material is elongated, like the strain rate is more here. That means we are trying to elongate the material. That is nothing but the drawing. That is nothing but drawing. So we will see what are the effects of drawing here. Drawing, what do you mean by drawing? Drawing means drawing stretches the polymer prior to the use. Even prior to the use, there will be stretching of the polymer, and it aligns chains to the stretching direction. In which direction you are stretching the material, it will get aligned in that direction. The chains will get aligned in that particular stretching direction. And what is the outcome of this drawing? This drawing increases the elastic modulus in the elastic modulus in the stretching direction, and the another outcome is increase the tensile strength in the stretching direction, but it eventually decreases the ductility. Ductility is nothing but the percentage elongation. It eventually decreases the ductility. And I have already explained what is meant by annealing, right? So annealing after drawing, what are the impacts of annealing or doing annealing after drawing? After drawing, if you make the material to undergo annealing process, then it decreases the alignment and it reverses the effects of drawing. Like the effect of drawing is stretching of the polymer, right? But if you after drawing, if you make the material to undergo annealing, again you can see the reverse effect of drawing, and it is same as the cold working in case of metals. It is same as the cold working in case of metals. See, in the previous slide you have seen brittle failure and plastic failure. Here we will see this elastomeric case. See, here the green line at the bottom shows you the elastomer case. Like, see, initial amorphous chains are kinked heavily cross-linked, and here in this region the deformation is reversible, and finally the chains are straight and still cross-linked. That means in the elastic region, like this is same as the elastic region. See, with increased strains the material is getting elongated. The material is getting elongated at very less stress levels. But when you unload the material, the deformation will be reversed in case of the elastomers. In case of the elastomer, the deformation is reversible in case of elastomers. See, up to this point we have seen the mechanical properties of the polymer. Now we will see the thermal behavior of the polymer. Thermal behavior is nothing but the behavior of the polymer when subjected to different temperatures. Okay, so here the behavior of the polymer is seen in two different characteristic temperatures, that are glass transition temperature Tg and melting temperature Tm. So what do you mean by this glass transition temperature? Glass transition temperature is nothing but initially you have a solid, for suppose a glass is solid in hand, but when you increase the temperature, as I said earlier, like if you take a plastic and if you increase the temperature at which the plastic material is located, what will happen from the solid or glassy stage, it will slowly go to this viscoelastic stage, right? It will slowly go to some viscoelastic state. But if you further increase the temperature, like if the temperature is further higher than this glass transition temperature, what will happen? The material will eventually undergo melting. That is nothing but the melting temperature Tm. That is nothing but the melting temperature Tm. So based on these, for suppose if you are going to use some plastic for regular use, or some other plastic for any purpose, you have to check what is the glass transition temperature and what is the melting temperature. Based on that, you can decide whether it can be used for hot temperatures or not, right? Whether you can use it for hot temperatures or not. For suppose if the melting temperature is very much less, then you can't use it. Like if the melting, that you can understand in the subsequent slides also, there are some examples given, so I will explain you there. And another two types of behavior which we are going to discuss here is thermoplastic versus thermosetting behavior. Thermoplastic is nothing but with increase in temperature, the material will will undergo this plastic deformation. But in case of thermosetting behavior, what will happen is it will not show any plastic deformation, but it eventually go for brittle failure with increase in temperature. That is thermosetting behavior. See, the glass transition temperature and melting temperature are explained here by taking three stages of a material, like amorphous, semi-crystalline and crystalline. Amorphous means the random nature of particles, semi-crystalline and crystalline. For suppose if you consider a graph between specific volume and temperature, specific volume is nothing but volume of the material to the mass of the material, that means inverse of the density. Okay, so this is specific volume on y-axis and temperature on x-axis, and on x-axis you can see in this is glass transition temperature and this is melting temperature. And see, for amorphous material, with increase in temperature, what is happening? The specific volume is getting increased, right? See, for suppose you take a container, and if you keep a solid in that container, the volume occupied by the solid will be less compared to if you transform the solid into liquid by heating it, the volume occupied by the liquid in the container will be more than the solid. So when the material is getting transformed from solid to liquid stage, the volume occupied by the material will be higher. That's why here with increasing temperature, the specific volume is also getting increased. For all the cases it is getting increased, but in case of amorphous material, what is happening is there is a transition which is shown here. Some from glass transition temperature, there is a transition and from melting temperature you can see the material has transformed into a liquid, but in case of semi crystalline the transition will be lesser, and uh, after melting point it is going to this liquid region. And in crystalline you can't see the transition at this glass transition temperature. You can't see any transition in case of this crystalline material. And this is the explanation for thermoplastic versus thermosetting. See, thermoplastics are will have little cross linking, whereas thermosets have large cross linking. That means 10 to 50% of nets will be present in case of thermosets. And thermoplastics are ductile in nature, but the thermosets are hard and brittle. That's why we can't see the plastic deformation or the ductile elongation in case of thermosets, and it will soften with heating and it will not soften with heating. The examples for thermoplastics are polyethylene, polypropylene, polycarbonate and polystyrene. And the examples of thermosets are vulcanized rubber, epoxies, polyester resin, phenolic resin. Okay, see here this is a graph showing showing the temperature versus molecular weight, temperature on y-axis and molecular weight on x-axis. And see, for a crystalline solid, this is for a crystalline solid, and this is for a, see, for mobile liquid, at higher temperatures the material is converting into mobile liquid, but here the molecular weight is very less. And in case of, this is the case of viscous liquid and this is the case of rubber, and from mobile liquid to rubber the molecular weight is increasing, and for crystalline solid it is at lower temperatures, and partially crystalline solid is at a bit higher temperatures than the crystalline solid. And between the transition between this glass transition temperature and melting temperature you can see a tough plastic here, See, this is thermoplastic behavior. This thermoplastic behavior will also depend on the temperature. For suppose at 4 degrees Celsius, here in the, you can see the blue line is showing a brittle nature. Whereas in 20 degrees Celsius, what is happening? It is showing like lesser brittle nature and more plastic, and at 40 degrees it is having lesser brittle nature than 20 and 4 and higher plastic nature. And then at 60 degrees it has higher plastic, the plastic region is higher in case of the 60 degrees Celsius. See, decreasing temperature, the effect of decreasing temperature, this is increasing temperature, and what are the effects of decreasing temperature? With decrease in temperature there is an increase in elastic modulus. See, elastic modulus is nothing but here if you take the slope of the curve you can get the elastic modulus. So with decreasing temperature the elastic modulus will increase, and it increases the tensile strength also. Here the tensile strength is more, but it has brittle nature, but the tensile strength is more, and it decreases the percentage elongation because it is brittle in nature. So it will have lesser percentage of elongation. So these are the effects of decreasing temperature. And with increasing strain rate, this is the increasing strain rate, and from increasing strain rate what you are able to see, the effects are same as decreasing the temperature. See, this is viscoelasticity. So for finding out the viscoelasticity nature of the material, we need to conduct stress relaxation test. stress relaxation test is nothing but, for suppose if you take bitumen and if you elongate it in the longitudinal direction, and if you elongate it in the longitudinal direction, and if the strain rate is maintained constant, if the strain rate is maintained constant, then what will happen is within the material, uh, the material will adjust the rate of stress. The material will adjust the stress concentration in it, and it will get relaxed, like the stress relaxation test. That means here, see, if you take the tensile stress and if you maintain the strain constant, there is a decrement in the stress with time. There is a decrement in the stress with time. This is known as stress relaxation. This is known as stress relaxation, and this relaxation modulus is given by the stress divided by the original strain. Stress divided by original strain. Okay, stress divided by original strain. And this is the, with increasing temperature, how the elastic modulus is varying, how the how the relaxation modulus is varying. See, with increase in temperature, the relaxation modulus is also getting decreased, because the stress relaxation will be more. That means the decrement in stress will be more. That's why the overall relaxation modulus is getting decreased with increasing temperature. See, the sample temperature values are like glass transition temperature for different materials is given here. So here it is -110, so it is much lower than this. Like for low molecular weight, the Tg is also very less, and for polyethylene with high molecular weight, it is -90, which is higher than this, higher temperature than this. And this is for PVC, this is for polystyrene, and this is for polycarbonate. See, till now we have seen mechanical and thermal properties, and now if you look into some engineering properties such as impact resistance, fatigue resistance, tear strength and hardness, the polymer will be much different from the characteristics of steel and concrete. When compared to the concrete or steel, the impact resistance and fatigue resistance will be and the tear strength will be lesser in case of polymers, and see, we have seen some additives for concrete, right? Admixtures, like we have named it as admixtures. By making use of the admixtures, we were able to alter the properties of the concrete. As the same here, there are some additives for polymers. By making use of those additives, we can alter the properties of the polymers. Like for example, fillers are used to improve the strength, hardness, dimensional and thermal stability, etc. Like the examples for fillers are fine sawdust, silica floor, sand, glass, clay, etc. So by adding these fillers, you can get improved strength, hardness and dimensional and thermal stability. And by adding additives such as plasticizers will obviously improve the ductility and toughness, like also the flexibility, and reduce the hardness and stiffness. Okay, and stabilizers will improve the resistance to environment. For example, from the UV radiation, oxidation, light, etc. And colorants are for dyeing the polymers, and flame retarders are used for interfere with combustion process or cause cooling of the burning region. Like when the polymers are in the burning region, the flame retarders will help causing the cooling, And composites, like, see, as such we can't, for suppose if you want to use polymers in construction, as such we can't use the you can't use the polymers because it will have like fire catching nature, and it is less resistant to the sustained loading. So the only way how we can use the polymers in the construction as a composites, as composites. For suppose, what do you mean by composite is, there are two phases here, matrix and dispersed phase. For example, if you take cement concrete, the here the if you take the case of cement concrete, here in the case of cement concrete, matrix is the cement. The cement paste is the matrix. So the cement paste will be in the matrix phase, and the aggregates will be in the dispersed phase. The aggregate will be in the dispersed phase. So the classification, when you see the classification of composite materials, the composites are classified into particle reinforced, fiber reinforced, and structural. In particle reinforced, large particles, again it is classified as large particle and dispersion strengthened. Okay, and in fiber reinforced, it is continuously aligned or discontinuous, and in structural, like laminates and sandwich panels, here particles will be introduced in the dispersion phase. In the dispersion phase, here the fiber reinforced, like small fibers of the polymer will be dispersed here, and in structural, these are used as some laminates or sandwich panels. And this rule of mixtures is defined to, like, for suppose if you have two phases, like if you have composite having two phases, phase 1 and 2, with modulus of elasticity E1 and E2, and volume fractions V1 and V2. Volume fraction is nothing but fraction, like V1 divided by the total volume, V2 divided by the total volume. Those are nothing but the volume fractions. And here you have upper bound and lower bound rules. Upper bound and lower bound rules is, for suppose, see, here the graph is, the data is for copper matrix with tungsten particles. Copper matrix, here the matrix is copper and the dispersed particles are tungsten. Okay, if you can see on the x-axis, here it is pure copper. It is pure copper, and here it is 20% of tungsten, 80% of copper, and 40% tungsten and 60% copper. This is so here this is 100% tungsten and 0% copper. So as you can see here, with increase in a percentage volume of tungsten, what is happening to the elastic modulus? The elastic modulus is getting increased. The elastic modulus is getting increased. But for suppose, if you want to get if you want to find out the elastic modulus of the composite, for suppose, for some, for here 40% of copper and 40% of tungsten and 60% copper, you can get the elastic modulus here at around 200 gigapascal. So it will be within this limit. It will not be greater than the 200 gigapascal. That's why this is known as upper bound. This is known as upper bound. See, you can see the upper bound and lower bound rule. Upper bound is parallel rule and lower bound is series rule. See, parallel rule, the two phases of the polymer are parallel or parallelly aligned, and it is loaded with this P is the loading, and so P is shared between P1 and P2. That's why P is equal to P1 plus P2, and the elongation epsilon is equal to epsilon 1 is equal to epsilon 2. So the elongation between the two phases will be equal. So by by converting this P is equal to P1 plus P2, by expanding it, loading is nothing but, like, stress is nothing but load by area, right? So loading is nothing but stress into area, so stress into area, which is equal to sigma 1 A1 plus sigma 2 A2. And by replacing this stress with epsilon into elastic modulus, and by simplifying, you can say that elastic modulus of this composite material which is aligned parallelly is equal to E1 into this area fraction of 1 plus E2 into area fraction of 2, that means E1 V1 plus E2 V2 when it is connected parallelly, that is upper bound. That's why you can see in upper bound rule of mixture, the elastic modulus of the composite is equal to Vm Em plus Vp Ep. That means volume multiplied with elastic modulus of the matrix plus volume multiplied with elastic modulus of the particle, like matrix and dispersed phase. And when coming to the lower limit, it is series rule. That means the materials are connected in series combination, and the unit area is equally shared between the two two units, but the overall deformation is the sum of deformation of the first phase and the second phase. So by simplifying this, you can get this lower bound. That means 1 by EC is equal to Vm by Em plus Vp by Ep. That means the rule of mixtures is defined to get the properties of the composite material, That's why the rule of mixture is used here. The particulate composites are particles of one phase dispersed in a continuous medium of another phase. Those are particulate composites. And large particle composites, example concrete, like if particles are big, for suppose if the matrix is cement and the dispersed phase is for aggregates, then it is large particle composite. And for dispersion strengthened, for suppose alloys, if you take the case of steel, it is a mixture of nickel and copper, but it has the particles are very small in size. That means from 10 in a size of 10 to 100 nanometer. So that's why it is dispersion composite, and concrete is a particulate composite. And see, these are fiber reinforced composites. The critical length of fiber orientation. The fiber orientation is important here. Here in the first picture, it is continuous and aligned in the direction of continuous and aligned, and in the second picture it is discontinuous but still aligned. That means the short fibers which are discontinuous but are aligned in one direction. The third one is discontinuous and random. That means there are short fibers and very random which are arranged in a random fashion, and the loading direction is both longitudinal and transverse. Like, see, why the loading direction and the fiber orientation are important. For example, if you take the case of wood, if the fibers are oriented in the direction of loading, then the strength of the wood will be much higher. But if fibers are oriented in the opposite direction to the loading, then the strength of the wood will be less compared to the fibers oriented in the same direction. That's why the direction of orientation is also important here. See, this is the example of fiber reinforced concrete. That means the concrete has a matrix and dispersed with some this fiber composites. And why the fiber length is important is this critical fiber length is important for effective stiffening and strengthening. More the fiber length, more the stiffening and strengthening nature of the polymer. Okay, see, the fiber length greater than 15 times the sigma f d by tau c. Like the sigma f is fiber strength in tension, d is fiber diameter, tau c is shear strength of fiber matrix interface. So example for fiberglass, fiber length greater than 15 mm is needed. And why it is needed? This like long fibers carry stress more efficiently than the shorter ones. Stress more efficiently than the shorter ones. See here it has a shorter length, that's why it has poor fiber efficiency. But when you have the larger length, you have better fiber efficiency, because with the larger length the tensile strength is also higher, and with increased fiber diameter the stiffening effect will also be higher. So this is the main purpose of this like fiber reinforced plastic in construction. Fiber reinforced plastic in construction. Why we have to go for this fiber reinforced plastic in construction? Already we are reinforcing the concrete with steel to take care of the tensile loads. But why is this alternative of fiber reinforced plastic in construction? Why are we going for that? Because to eliminate the major problem concerning with the steel reinforcement. What is the major problem we are concerned about in steel, in case of steel reinforcement? That is nothing but corrosion. That is nothing but corrosion. So if you replace the steel reinforcement with the fiber reinforced plastic, then we can get rid of this corrosion. But we have to take some care while using this fiber reinforced plastic in construction. See, why use of FRP, fiber reinforced plastic? Because the main problem with conventional steel is corrosion, right? This available corrosion repair and preventive methods are expensive. For suppose if you want to go for non-destructive testing or destructive testing in case of some like steel reinforced concrete structures, it is very expensive. It is very expensive and time consuming also. So, and that's why we are in need for alternate solutions. And what is this FRP? It is like fiber reinforced plastics are composed of natural or artificial fibers embedded in a polymer matrix. See, here we have seen that embedded in a polymer matrix you can see some short fibers which are natural or artificial in a polymer matrix. So the properties of the composite are related to the properties and volume fraction of the individual phases. We have seen in the rule of mixtures, right? So it will be, the properties will be related to the volume fraction of the individual phases. And the different types of common reinforced fiber reinforced plastics are GFRP, like glass FRP, carbon FRP, aramid FRP, and FRP is usually manufactured in India, and only this glass FRP will provide a cost effective alternative to steel for construction purpose, because if you want to go for this carbon FRP and aramid FRP, it won't be cost effective. That's why the only replacement for steel in the construction purposes is glass reinforced glass fiber reinforced plastic. Okay, so here there is a comparison between the glass fiber reinforced plastic versus structural steel. What are the advantages of glass fiber reinforced plastic over the structural steel? The main advantage is no corrosion, and then higher tensile strength. Like strength is a function of bar diameter, we have already seen. The tensile strength of fibers is much higher than that of the composite, and it will have lighter weight compared to the structural steel. It will have lighter weight as compared to the structural steel. But the major disadvantages are it is brittle nature. We have seen that in the like stress strain characteristics. It is brittle nature, and it will have lower stiffness, like 25% lesser stiffness than the steel. So deflection checks are important. Obviously the costs are higher, and the uncertainties about fire resistance, long term creep, and resistance to aggressive chemical environment. So we have to take care of all these concerns, like whether it is fire resistant or like the polymers are not as it is a plastic, we can say it will easily go for this melting temperatures, so it is not fire resistant. And for long term sustained loading, it will undergo creep deformations, and when it is mixed with some aggressive chemicals, it will have some adverse reactions. Okay, so these are all the disadvantages. So while using this glass fiber reinforced polymer, we have to take some certain precautions so that you can avoid these uncertainties. See, these are the stress strain characteristics for glass fiber reinforced plastic, aramid and carbon. These are all ductile in nature. These are all brittle in nature. There is no ductile region here. But when you mix it with reinforcing steel or pre-stressed steel, it is having some ductile nature. It is having some ductile nature. So the applications of FRP are pre-stressing of bridges, retrofitting with FRP laminates, filament binding and structural wrapping, uses of fiber in structural composites. For suppose, see here, the applications are when you go for this bridge construction, here the black color stripes you can observe, these are this FRP, the GFRP materials, and when you incorporate these materials in this direction, in this longitudinal direction, what will happen is it will take care of the tensile strength. It will take care of the tensile strength uh, when the beam gets deformed with some loading on it. So it will take care of the tensile loads. It will take care of the tensile strength, so that the material will not, the concrete will not fail in tension. And if you arrange it in this direction, it will take care of the shear stresses. It will take care of the shear stresses. That is the major applications of FRP. And it can also be used as structural composites as laminates. For suppose if you take a plywood, as I told you earlier, wood will have higher strength only in the only when the grains are in the direction of loading. But in case of this structural composites such as laminates, what we are doing is we are taking laminates in which the grains are oriented in different directions. For suppose in the first sheet, you can see the fibers are oriented in this direction. In the second one, those are oriented in this. Likewise, so in every direction, you can have the laminates. And those can be attached with the plywood, so that in every direction, whatever might be the direction of loading, you can say there are high. It will have higher strength in that particular direction. That is the major use of these polymers as structural composites. Like here also the sandwich panels also. For suppose on the this is the face sheet, and this is the intermediate sheet, which will have lesser strength but will have more adhesive properties. This is the use of structural composites as sandwich panels. So in this week lecture, what we have gone through is what do you mean by polymers, and what are its mechanical properties, what are its thermal properties, okay, what are its thermal properties, and what is a tensile response when subjected to some tensile loading, and what do you mean by glass fiber reinforced plastic, and what are its advantages over conventional steel, and what are the different types of structural components which can be used in construction. These are the things which pertains to the contents of week 9. So if you have any queries related to this particular lecture, you can feel free to ask now. Any queries?
Hello.
Yeah, tell me. Hello. Yeah, do you have any doubt to share?
Ma'am, hello. Am I
Yeah,
audible?
yeah, tell me.
Ma'am, so actually, in the assignment for the week that we are supposed to submit tomorrow, which I believe is week 10, there are two questions for which the main figure is not given, the question number 5 and question number 6.
Okay,
So for them, the figure is not given at all. So I have
okay,
mailed also regarding this, but I
okay.
haven't got a response. And since we are supposed to submit the assignment tomorrow, could you please check into that and let us know?
Yeah, okay. Even I have to email the NPTEL people once because we can't have direct connection with the matters regarding this. I'll try speaking with them and I'll let you know. Okay?
Sure, ma'am.
Yeah.
Ma'am, actually, that has submission tomorrow, so it's a bit urgent as well on our side.
Oh, okay, fine. I'll try from my side. If at all, if I get any response, I'll let you know. Can you send me your
Sure, ma'am.
mail ID here?
It's tkhajuria25@gmail.com. I'll just type it over the chat
Yeah,
box.
yeah, sure. Yeah, thank you.
Yes, ma'am.
Okay, fine. Okay, I'll let you know if I get any response from their end. Okay?
Sure, ma'am.
Okay. So, if you don't have any queries regarding today's content, can I close the session?
Yes, ma'am.
Okay, thank you. Thank you, Tushar. Thank you, everyone.